In this video, I will go over the homework that follows the lecture 18.2 that covers a few applications of separable differential equations. And as always, I hope that you watched this lecture, and let's go ahead and jump right into the homework. We have the following problem presented to us, and if we read it, what do we understand here? We understand that, well, we clearly have some equation here, and we clearly given k, even with some units here. We're also given the fact that there are 500 milligrams of antibiotic initially, so that means if y represents I guess we need to make an assumption that y represents the amount of antibiotic. So y of 0 is equal to 500, right? And then we can plug in k, which we can do any time. So let's just focus on solving the equation. So we have 1 over y dy equals to negative k dx. We integrate because it's a separable differential equation. On the left side we have ln absolute value of y. On the right side we have negative kx, and we have plus c over here, and it's a pretty standard solution. So let's call it c1. Let's raise everything, let's exponentiate everything, e to the power negative kx times e to the power c1, which we now call c2. Then we can get rid of the absolute value here because it's always positive, and we have this. K is given. Now to find c, we're going to use the initial condition, and that is equal to 500. And the only way that will be equal to 500 is if c is equal to 500. So the solution is 500 e to the power negative kx, but now we can use the fact that k is 0.0866x. So that's the answer. And now the question is how much we have after 14 hours, which is pretty much we're just evaluating this function at 14. And to do this, I'm going to grab a calculator. Desmos will do. And here I'm just going to type exact that expression. And the answer is that's not the right answer. To find the right answer, we have to probably put 14 right over here. So 148.74 milligrams, I assume, are the units, but let's see. Yeah, so 148.74. All right, so let's take a look at another problem. This is an example of Newton's law of cooling, which I covered in actual lecture. So before we jump into this problem, you can refresh your memory by watching this lecture. Pretty much if we let T be the temperature of the whatever that is we're pulling out of the oven here, then let's read it. So a cake is removed, so that means at 0 the temperature is 425 degrees. The temperature of the kitchen is 70, So this is the temperature of surroundings. 10 minutes after the cake is removed, so T of 10 is 275 degrees. And we want to wait until the cake is cooled 80 degrees, right? So we want to find time when temperature is 80 degrees, right? So this is kind of the layout of the question. And the temperature, or how fast the temperature changes with respect to time, will depend on the difference between the temperature and the medium surrounding it in the following way. So it's going to be K, some coefficients which we have to determine. T is the temperature, and here goes the temperature of the medium, which we're told was 70 degrees. So this is the equation that describes the behavior of the temperature of this cake. Now, you notice that it's a differential equation. You can also notice that it is separable. And to solve it, we follow this method. And here we have ln of t minus 70 is equal to kt plus c. We have, let's exponentiate everything. So we have t minus 70 e to the power kt times e to the c. Let's call this c1. And t is always positive, so we can just drop the absolute value. Or rather, t minus 70 is always positive because the temperature of the cake is always above 70 degrees. So we can just drop that. We have some constant here. And the final step is we just add 70 to both sides. And we can just compare this with the lecture. We kind of follow the same steps as in the lecture, right? So there's nothing really new here. So now, in order for us to find the function, we have to compute c and t, and this is where we're going to use the fact that t of 0 is equal to 70 plus c e to the power 0, which is 1. So it's just literally 70 plus c, and all that will be equal to 425, meaning that c is equal to 355. And now that I know c, I can use the fact that t of 10 is 70 plus c, which is 355, times e to the power k that I don't know times 10, which would allow me to find k. And to find k, I just have to do some simple algebra here. And I'm going to isolate k. Oh no, sorry. I have to use the fact that all of that is equal to 275. So now I'm going to subtract 70 from both sides. So 355 e to the power 10k is equal to 205. So e to the 10k is equal to 205 over 355. 10k is equal to ln of 205 over 355. And therefore k is equal to 1/10 ln of 205 over 355. And this is something that we can compute. or we can use this exact value, and hopefully it will simplify to something nicer. But let me see. So approximately will be negative 0.0549108. And now we have a formula, right? So we have T, the temperature, as a function of lowercase t, the time, is equal to 70 plus 355 e to the power kt, but k is equal to negative 0.0549108 t. And the question, what was the question asking? The question was asking, we need to find t, the lowercase t, so that the uppercase t is equal to 80 degrees. So we're going to set all of this equal to 80, and we're going to isolate t. So we're going to subtract 70 from both sides. For short, I'm going to use k here instead of that long number. E to the negative kt is equal to 10 over 355. So we have negative kt here. Actually, k is negative, right? So I don't need the negative here because negative is part of k. So kt is just ln of 10 over 355. So t will be 1 over k times ln 10 over 355. And actually, this we can just put in a calculator now, right? So this is my k, and my t is equal to 1 over k times ln of 10 over 355. And it looks like the answer is quite nice. So it's 65001.006, and it's in minutes, I assume. Let's go back to the problem. T is in minutes, so if we have to round to the nearest minute, then the answer will be just 65 minutes. So we got that. All right, looks like we have another Newton's law of cooling. So hopefully this time it will go faster. Problem number 3. We have initial temperature 200 degrees. Again, T stands for the temperature at time t. T is in hours, and as I'm reading, I'm going to summarize it. So T of 0 is 200. After 1 hour, it was 110. The temperature of the medium surrounding the ice cream base is 5 degrees. And the question is to find the time when the temperature is 25 degrees. That's the problem. Now we're going to use the Newton's law of cooling, which states that the temperature changes proportionally to the difference between the temperature and the medium. So the larger the difference, the larger the faster it will be changing. And if the difference is negative, then k will be also, I guess, negative. So yeah, let's solve it. So we're gonna acknowledge that it's a differential equation. It's separable, so we have 1 over t minus 5 dt is equal to k dt. We have ln of absolute value of t minus 5 equals to kt plus c 1. So we have, cutting some corners here, t will be equal to 5 plus c e to the power kt. And now this is my general solution. Now I'm going to use the fact that t of 0 is equal to 200. That means c is equal to 195. Now c is equal to 195. We can use the fact that t of 1 is equal to, on one hand, 5 plus 195 e to the power k, and on the other hand, it's equal to 110. Now we can take this equation and solve it. So e to the k is equal to 105 divided by 195, meaning k is equal to ln of 105 divided by 195. Last time we did find the approximation of it in decimal form, but we didn't use it, so let's just keep it this way this time. And let's plug everything into the original equation. So the temperature is equal to 5 plus 195 e to the power t times k, which is ln of 105 over 195. And the question was to find t when the temperature is 25. So let's set it all equal to 25 and let's solve this equation. So we have 195 e to the power tk. I'll just go back to k to save some time. This is equal to 20. E to the power tk is equal to 20 over 195. And tk is equal to ln of 20 over 195. And t is equal to 1 over k times ln of 20 over 195. And this is where the fact that k is equal to ln of 105 over 195 matters. So this is the final computation. And I'm going to let Desmos do all of this. K is equal to ln of 105 over 195. And it's going to be 1 over k, ln of 20 over 195. So it looks like the answer is 3.679 hours. And the question was asking us to round to the nearest tenth. So the answer will be 3.7 hours. Which is good to know. All right, so this was problem number 3. Let's go to the next problem, number 4. Here we have a mixing problem, and when you're doing mixing problems, it's important for you to draw like a diagram. So here's we have some reservoir of water, and so for this problem, whatever we dissolve in the water, we define that to be our function. So let S of t be the amount of, and what are we dissolving here? Some pollution, right? The amount of pollution or polluting matter in the lake. And in kilograms. And as we're reading the problem, what do we learn? We learn that there are 40 kilograms of it at the beginning, so S of 0 is equal to 40. What else do we learn? We learn that there is 250 kiloliters of water. So this is the lake, 250 kiloliters of water. And it enters at, and the rate is 0.2 kilograms per kiloliter. And it is 10 kiloliters per day. At the same time, the solution leaves out of the river or out of the lake at, so let's go, so it leaves at also 10 kiloliters per day. And it's well mixed, and the question is find the algebraic expression for the total amount of polluting matter in the lake. So we just need to solve this equation. And I guess the answer here is u of t, so they suggest us using letter u here. I guess u stands for pollution. It really doesn't matter, just pick your favorite letter and use it. Now, this is what we have. Now, how do we set up the equation? The equation is set up by us looking at the rate of change of the polluting matter in the lake. And here we actually have to also notice that it's at time t, and t is measured in days. So we're considering du dt, which is the rate of change of the polluting matter in the lake. So the rate of change of the polluting matter in the lake is computed by how much of it comes in minus how much of it comes out. So it's the rate of the polluting matter coming in minus the rate of the polluting matter coming out. And that's how fast it's changing overall. Now, how fast is it coming in? Well, it comes in at 10 kiloliters per day, but there are 0.2 kilograms in each kiloliter. So this is how much of it comes in per day. So the units of 10 are kiloliters per day. The units of 0.2 are 0.2 is the quantity. It's kilograms per kiloliter. And then kiloliter cancels. So the units here are kilograms per day, which is exactly the same units as what we have on the left. So everything is in kilograms per day. So that's how fast it comes in. Now, how fast does it leave? Well, it leaves at 10 kiloliters per day, but what is the concentration of the matter in the lake? Well, at any given moment, there are not S of t, but u of t, much of it. But we need to divide that by 250 kiloliters. So here we have units kilograms per kiloliters, and these are again kiloliters per day. So after kiloliters canceled, we have kilograms per day. So this is the differential equation that we set up that describes the behavior of function u. And now that we have it, let's go ahead and rewrite it in a nicer and cleaner way. And now let's recognize that we have a differential equation that is actually separable and that we can solve. So let's find the common denominator here. And let's separate the variables. So we have, I'm going to move 50 minus u to the left. We have du over here. I have 1 over 25 dt over here. We integrate, and we have negative ln of 50 minus u on the left. On the right, we have 1 over 25 t plus c. We exponentiate, so we have e to the power 50 minus u. Sorry. Let's get rid of the negative first. So we have ln of 50 minus u equals 1 over 25 t minus c. Now let's exponentiate. So we have 50 minus u is equal to e to the power 1 over 25 t times e to the negative c. So let's call it c1. So now we can call this c2. And then u is probably not going to be like, let's get rid of the absolute value here. So assuming that u is less than 50, that's the assumption that we're making here, u is less than 50, then which is a fair assumption because we start off with u less than 50, then this is what we're going to get. And now isolating u, here's what we get, 50 minus, and since this is the last equation, I'm not going to write the index near the constant, so this is my function. I forgot the negative. Hopefully that's the only thing I forgot. Because... No! I forgot it was an initial value problem. Oh my god. U of 0 is 40. Oh my god. No. No. Not another one of this. So this is how you would finish this problem if you are not in a rush. Oh my god. Let's do another one of this. because hopefully it's just another one, not another cake. Oh my god, this, I ruined it. 4, so it's going to be a cake problem, and then it's going to be another one of those lake problems. Okay. All right, so we have a cake. So T stands for the temperature at time T. T here is in minutes. We have T of 0. It's equal to 425. After 5 minutes, it was 375. The temperature of the kitchen is 70 degrees. And the question is to find T when T of T is equal to 75. So Newton's law of cooling is equal to K over T minus 70. We have 1 over T minus 70 dt is equal to K dt. Integral ln of T minus 70 equals to kt plus c. So T minus 70, let me just cut some angles here. T minus 70 is going to be, so T would be equal to 70 plus c e to the power k t. Now we can use the fact that T of 0 is 70 plus c equals 425, meaning that c is 355, and T of 5 is equal to 70 plus 355 e to the power k times 5, which is 375. Then we solve it for k. K will be equal to 1/5 ln 305 divided by 355. That's my k. So now that I know my k, I can set up this equation. So T of t is equal to 70 plus 355 e to the power kt equals to 75. So we're going to be solving for t. T will be equal to 1 over k ln of 5 over 355. And finally, we can now plug the k in. K is 1/5 ln of 305 over 355 times ln of 5 over 355. And we are rounding to the nearest minute, so I'm just going to throw it in the calculator and be done with it. So k is 1/5 5 over 355, and formula here is 5 over so the answer is 140.30, so 39, so it's like it's gonna be 40, 140.40. Number 6, have this equation. K is given to us. Initial condition is at 0. The value is 50. The question is to find y evaluated at 11. That's the question. So we're going to solve this equation. We have negative 1 over y dy. I guess it's better to keep the negative on the right side. So we have ln absolute value of y is equal to negative kt plus c. So y is equal to c e to the power negative kt. It's not the same c as this one. To find c, we're going to use the initial condition. And which now means we have the complete function. And now we can evaluate it at 11. And now we can use the fact that k is equal to 0.0866 times 11. So the answer is 19.287. And the question was round the answer to 2 decimals, so 19.29. So another mixing solutions problem. The key is to draw a nice picture. Here we have, we use U. So U represents the amount of sugar at time t, and t is in minutes, and the amount of sugar is in kilograms. And the volume of the tank is 50 liters, and initially it has 7 kilograms of sugar. And there is a incoming stream at 5 liters per minute of a solution with concentration 0.3 kilograms per liter. And then at the same time it comes out at the rate, what's the rate? The rate is the amount of sugar divided by 50. That's the current rate, concentration of sugar, and it comes out at the same rate of 5 liters per minute. So if we're looking at the change of U with respect to time, it's going to be equal to the incoming sugar, which can be computed by taking 0.3 and multiplying it by 5, and subtracting the outcoming sugar, so which can be computed by taking the current concentration at time t and multiplying it by the rate at which it pours out. So this is the equation. We can simplify it. We can rewrite it like this. Or we can even find the common denominator and write it like this. And now we can recognize that this is a separable differential equation. And this is what I didn't do last time. Forgot that it was an initial value problem. And let's solve it. So we have du, we divide it by 15 minus u, and on the right side we have 1 over 10 dt. So throwing the integral here and there gives us negative ln of 15 minus u being equal to 1/10 of t plus c. Applying the negative to both sides gives us this. It may not be the same constant, so exponentiating. Again, not the same constant, but we've seen this transformation before. And getting rid of absolute value, u is less than 15. That's a fair assumption because we start at 7. And once we get rid of absolute value and simplify, this is what we get. Now, no rush. Let's plug in 0 in here. That means c is equal to 8. So the final answer is 15 minus 8 e to the power 1/10 t. And I forgot the negative, just like last time. And we completed this assignment. And if you have any questions, please feel free to reach out.